Okay, in this video we'll be talking about the last of our rotational motion topics, and that is angular momentum. You've noticed at this point that every time we talk about something in rotational motion, we try and relate it back to its translational motion counterpart, or regular motion, the stuff you studied at the beginning of the year. So angular momentum is the same sort of thing. We studied momentum at about the midpoint of the year. We know that momentum is equal to mass times velocity, and we know that it seems like a strange combination of things, but there are conservation laws that apply to it. In certain situations, momentum is conserved. That all is pretty much true for angular momentum as well. Just like linear momentum, angular momentum, which is symbolized by a capital L, is useful for situations in which collisions or interactions cause objects to rotate, to move around some central axis. That is why we care about angular momentum, okay? Linear momentum, regular P, that was useful in collisions where we had two objects moving in a certain direction or in certain directions and they hit and we want to know what happened at the end. Angular momentum is good for the same sort of thing, except we care, the final or initial state is not necessarily just moving linearly or translating, but also an object that rotates. The equation, the main equation, just like P was equal to mv, L is equal to the rotational motion analog of mass is moment of inertia, which is I. And instead of v, which is linear velocity, we have angular velocity, which is omega, which I sometimes jokingly like to refer to as wumbo. So you're going to have to deal with me saying wumbo and being silly. All right. So angular momentum is equal to the moment of inertia multiplied by the angular velocity. And again, why do we care about these quantities? They seem really random. It's because someone discovered at some point that in certain situations, the angular momentum of a system is conserved. So L equals IW, or excuse me, omega for a point. Sorry, I'm just reading my notes here. Okay, so that is the general equation, and we also have some other. I have another equation that I would like you to memorize. I believe this is on the reference tables. Something you should have in your head, though, is as follows. For a point object, remember, a point object is just like, you imagine like a infinitely small point, okay, or something that can be reduced down to a point. For a point object rotating around something, some central axis, recall what the moment of inertia is for that. We have talked about it before. The moment of inertia for a point object is I equals mr squared. Okay? Remember, moment of inertia essentially tells you how hard it is to get something to rotate around a particular axis. For a point moving around some sort of axis, the moment of inertia is the mass of the point object multiplied by the distance away from the axis squared. Recall this moment of inertia for a point object, and that linear speed, linear velocity, is equal to the radius multiplied by the angular velocity. So this isn't in the reference tables, but it is good to know, especially for our upcoming gravitation unit. The angular velocity of a point object can be given as follows. If I for a point object is mr squared multiplied by, let's see, omega must be v over r. One set of those r's is going to cancel out. And that means that the angular momentum for a point object is m times r times v. okay? And that is actually kind of important. So we can calculate angular momentum for point objects. This is like if balls or spheres or other round objects are moving around some sort of axis, we can calculate their angular momentum. And again, that's useful because there is a conservation law that applies with this. What happens if you have multiple objects that have angular momentum? If more than one object is rotating, you can add or subtract the angular momenta as necessary. Now, when would you add, when would you subtract? If you have if they're rotating in the same direction, so we could say counterclockwise, then we can add the momenta together. If one rotates clockwise, the other rotates counterclockwise, we would say that one is positive and one is negative. Again, remember, counterclockwise is typically the one that we pick to be negative. Okay? And this kind of goes along with that. So just a little note. A lot like torque, angular momentum has to be defined with respect to something. So that essentially what that means is that you need to specify an axis of rotation. Okay, you have to say what it is rotating about or what it's revolving about. You can't just say something has angular momentum. You have to say with respect to what. Okay, this ball doesn't just have angular momentum; it has this much angular momentum with respect to this pole that it is moving around. All right, so we have this idea of angular momentum. It's the rotational equivalent of linear momentum. There are conservation laws that apply with it, and let's jump into those. So let me give you an example question. Let's say that we have a mass of little m is moving with initial velocity v and it strikes an object of mass capital M at one end. A distance L over 2 from its center of mass. So let me draw the picture of that for you. We have, here's little m, it's like a little sphere. And it's moving with a speed of v, and it's about to strike this rod, this object that looks like a rod. And this object has a mass of m, and this whole thing has a length of L. So the center of mass is right here. That would be L over 2 away from it. We are going to assume a perfectly inelastic collision and that little m is much smaller than big M. So we're going to make a couple of assumptions here. And we want to find the velocity of the center of mass and the angular speed, the angular velocity after the collision. We're going to put in here if rod is free to move and rotate. That's how it would be phrased. Okay, so it is important that we say if the rod is free to move and rotate, because if it's free to move but not rotate, that means it won't spin. If it's just free to rotate but not necessarily to move linearly, then that means it's like pivoted about one end and it'll just spin like this. Having it free to both move and rotate means that this rod will not only move to the right, like the whole thing will move to the right once this mass hits it, but it'll also spin and rotate some. So, if, oh, and also, I forgot, we're going to assume that this object rotates about its center of mass. Okay, so we're going to assume that the center of rotation is right here. We're not like one end isn't being held in place and the other is spinning. So, if M is completely free to move, then both linear momentum and angular momentum are conserved, which means they're the same both before and after. Okay? Now the tricky thing about this is if you were to ask, well, how fast is this object moving? Well, you'd get different answers depending on what part of the object there is. You can imagine, imagine taking like this pen, setting it down on a frictionless surface and pushing it and spinning it at the same time. If you were to track different parts of the pen, some parts would be moving very fast at other points, other parts would be moving very slow, and the parts of the pen that are moving at these different rates, linear rates, would change. So obviously, different parts of this translating, which just means moving in a linear fashion, rotating object plus mass will have different linear speeds. That's what I was just saying. Different, like if you could imagine different little points, if you were to mark in a bunch of little points on this rod, they're going to be moving at different speeds at different times. Okay? However, when we apply conservation of linear momentum, the velocity in that equation refers to the center of mass. Okay, so we have two different situations here. Let's deal with the easy one first. If linear momentum is conserved, well, we know how to deal with that. That's easy. The initial linear momentum must be equal to the final linear momentum. This just means there's no net force on our system. Initially, there's an object of mass m with a speed of v. I probably should have labeled this v naught. Yeah, let's do that. Okay. So we have mv naught equals, at the end, we now have a combined object of little m plus big M moving. And this v is the velocity of the center of mass. So I'm just going to write vcm. And if I solve for that, that's pretty easy to do. We end up with vcm equals little m times v naught over the now combined masses, little m plus big M. That's a result that you've seen many times. Now, figuring out the angular momentum is a little bit trickier, but we still know that it is conserved, so we're going to start with this, L equals L naught. Now here's where you might get confused. You might say, but wait a second, this object isn't spinning at first. How can it have angular momentum? Because we know it's going to spin after the collision. If you're saying that it's conserved, where does this initial angular momentum come from? So the question we're looking at is, how does the mass initially have angular momentum? It turns out that objects actually don't need to necessarily be rotating as you think of it to have angular momentum. Instead, what we're going to do is we're going to assume that this mass right here is what has the angular momentum. So we're going to use L equals mvr, with r being the distance from what I will call, and you've seen this term before, the line of action, which really just means the initial path of the mass, to the axis of rotation. So this is kind of something, it's a little bit similar of a thought process to torque. When we come back, I'll show you the calculations that you need in order to make this work, and I'll explain about this a little bit more.